Alrighty, so let's talk about that do now question because it's a really common question you guys can get on the exam. I'm only talking to a handful of you, I know. So, because a lot of people are away today. That's okay. So with the do now question, I want us to think about with chemical reactions, why is it important to think about the states, in particular with water? Because you can see that water in some chemical reactions can be produced as a gas versus as a liquid. And if it is produced as a gas, why is less energy being released in that same reaction? So it's exactly the same reaction. The only thing that's different is that the water product, instead of being in a liquid, is in the gas form. This is a really common question I like to ask on these exams. That's why I want to bring it up as a do now. And the reason has to do with the fact that the energy that would have been instead released from that chemical reaction is being used to break the bonds to make something go from liquid to gas state. So the energy is being used for phase change instead of being released in the environment, which is what the exothermic reaction would be. Are we okay with that? Does that make sense, Miguel? Okay. Cool. So the next thing that we're going to be talking about for today then is looking at the two-step enthalpy calculations. They're similar to what you guys would have done last year for structure and bonding. The thing that's different, though, is that these have a more complicated setup, so we have to be mindful of what we're reading and how to set up that up properly. With the enthalpy calculations that you're going to see for this year, for that section, it's going to fall into three categories. So there's three different versions of how we do this question. I'm only going to show you one version. The first version is thinking about we are heating actually I'll show you it on the piece of paper. You guys can start seeing it. So this is the first example. You are burning some sort of fuel and you're heating water. So that's the first type of example question that you're going to get. The second one could be then you are dissolving something into water. So you're taking a substance like salt, you're adding it to water, you're dissolving it, you're measuring the temperature change. So that's the second version of the question. These two are the most common ones. The third one is the neutralization one, which you are mixing two solutions together and you're measuring the temperature change as well. So those are the three you're going to get. Those are the three potential ones that you're going to get. They only really ask one out of those three on the exams, maybe two if they're feeling nasty, but that's what we're kind of thinking about for today. We okay so far? All right, so my plan then for today is I want to show you how to do these two-step calculations. I've talked about three different versions, so now all we're thinking about then is let's look at this on an exam schedule just to kind of see what this looks like. On an exam question, see what this looks like. So I'm going to pass this out to you guys, so that way we can do the math. All right, and I put one on my desk too. Cool. I also want to grab. I don't think I have to. All right, I'm very mindful. What I have in the house. All right. Cool. So, actually, let me bring up the resource sheet so you guys can see what that looks like. Because they used to not give you guys the equations, but they would give the equations for physics, which I thought was really weird. Level 3 street resource sheet. So that way we know. There we go. Okay. So, just so you guys are aware of what you're going to get on the chemistry exam, resource-wise, so you don't have to worry about memorizing equations of sorts. So this here is the formulas that they plan to have you guys use for the thermochemistry external. So they do provide you those. You just be mindful of what you use and when you use them. We are looking at using basically these two today and potentially maybe these ones depending on the style of question. We have looked at previously this one, which we talked about. If you had everything in formation, you can take the sum of the products minus the reactants. So let's unpack this question and then figure out how we're going to use those equations there. So the thing we have to keep in mind when we are looking at this question here is there's actually two sections to this question. The first section is thinking about this little burner and that chemical reaction of burning that oil or that fuel in order to get heat. And then the second part of this equation that you're looking at is this top bit here, which is the heating of the water. So we have to be mindful that there's two different sections of this equation, and we're going to have to grab different numbers depending on what we're trying to do with our calculations. So that's why I'm saying it's a two-step problem. It's very different from last year where it was one combined step. You were looking at a chemical reaction doing your calculations. In this case, you have to factor two things together. So we do need to keep in mind what is what when it comes to our knowns and our unknowns and where is it coming from, so we're grabbing the right numbers. So I'm going to do some color coding just to help keep track of that. The other thing I like to do as well is, this is a trick I learned when I was in high school taking physics, is how to organize your thoughts. So I like to create a list of knowns, so I know all my known values that I've gathered from the question. I then think about what my unknown is and what I'm trying to solve for, and then I can then pull what equations I need. So really useful kind of skill set if you are taking physics, because there are lots of equations that you are given, and you need to make sure you organize things properly. Are we okay with that so far? All right, so the first thing I'm looking at is that a student is burning 2.28 grams of liquid methanol. So that is talking about this reaction here. And they're trying to heat 100 grams of water. So that's talking about what's up here. So that's why I'm highlighting them in different colors. So I do suggest you do that on the assessment, so it helps you, again, keep that mindset. The initial temperature of the water is 20.06 degrees Celsius. Once all the methanol has been combusted, so that's an important thing to be mindful of, is that you are using all the methanol there. Sometimes in these questions, they'll say the initial mass of the ethanol was this and the final mass was that. You need to do a subtraction to figure out the difference. So do keep in mind you are looking to see how much of the methanol you're actually using. So since that's telling me that's all the methanol it's using, then I can know what the mass of my methanol is. So I could do mass, and this is of the methanol. Should be an A, and my mass is equal to 2.28 grams. So I'm already starting to make notes of what things are. I'm also, like I said, trying to keep organized. The mass of the water is something I can also write down. So mass, and this is of the water, is equal to 100 grams. So I want to make sure that I know which one's which, because I'm going to need both of them with my calculations. It says the initial temperature is 20.6. So let's see what it says about what we're looking for. So all of the methanol has been combusted. The student correctly determined the experimental enthalpy change for the combustion of the liquid methanol, and the combustion of the methanol is negative 86.2 kilograms per mole. So what that tells me there is it's telling me how much energy is going to be released. So that is my delta CH, and that's negative 68.6 kilojoules per 1 mole. That information there. The specific heat capacity of water is 4.81. This is a constant. So I would go C is equal to 4.18 joules per gram per degrees Celsius. And then it's also giving me the molecular mass of the methanol. So big M of the methanol, CH3OH, is equal to 32 grams per mole. So I don't have to worry about doing that calculation there. They want you to calculate the final temperature of the 100 grams of water. So that is my unknown, final temperature of the 100 grams of water. So my unknown is the temperature final. That's what I'm trying to figure out. I do have the initial temperature. So the temperature that is the initial value is the 20.6 degrees Celsius. So that's all the information that I'm looking at right now. Are we okay with that so far? All right, cool. Let's now start looking at those equations that they've given us to think about how are we going to work backwards to figure out that temperature change. So what I see here is I see certain values that I can use. So we have the delta H. We have an N value, we have a Q value, we have a Q value here, an M and a C and a delta T. We also have N equals M divided by M. So these are all equations that I'm looking at using to tackle this question. First thing I'm thinking about is what I've been given is in grams, so I need to convert the grams into moles, because once I have the moles, I can then start using them for other bits and pieces. Are we okay so far? All right. So I'm going to need 3 equations. The first equation I'm going to be using is this guy here because I need to convert my grams into moles. So I can't have anything that's currently in the grams sector because that means I can't actually do any of my calculations because everything unit-wise, if we look at the units, is all in, you see, moles and moles. So I need to convert that. That's my first step. So the first equation I'm going to be using today is going to be the n equals little m. Oops, let me make that. N equals little m over big M. Let me write that one down. Cool. All right, so I know what my little m value is, and I know what my big M value is. And this is, again, why it's important to make sure we have organized what is from which half of the reaction. So you see how there's 2 values for M? There's going to be different instances when I want the different ones. So that's what I got to be mindful of when I'm looking at this. So in this case, because we are talking about the reaction of the methanol burning, I want the methanol mass. Are we okay with how I figured that out? All right, so let's start setting that up. N is equal to my 2.28 grams, and I'm dividing it by my molecular mass of 32 grams per mole, like that. Are you okay with that? I like to always put my units in when I'm working because it's a really good way to idiot check myself. Because if I can make sure that the units cancel out, then I know I've done the step correctly. So I've canceled out my grams, and this is per mole because it's underneath the division sign, so now it becomes mole again, which is what I want as my unit. So I'm going to grab my calculator, so that way we can do that math. So remember where my calculator is there. All right. So I am doing 2.28 divided by 32, and I get my N value for, again, the methanol. That's methanol. Yep. Is equal to 0.7125 moles. Are we okay with how I did that? Yes? All right. Now, this is what I'm saying. The difference between this year and last year is that there's multiple steps to this, and we have to use multiple equations, and we have to know why we're using it and when we're using it. It's going to change color so we know which equation we're using next. So when I'm thinking about this, I want to find the change in temperature. So this here is my final step. This is my final equation I'm going to use. I have everything I need in there. I have the mass of the water. I have the heat capacity of water. I have the initial value of the temperature. I do not have the final value of the temperature. Are we okay with that? So my final temperature is my unknown. The other thing I do not have is the Q value. Do we see that? So I need to get the Q value. So now I'm going to be using this equation here. So think about it as a sequence of what you're trying to do and then what equation you're going to grab. So I'm going to grab this equation here because I now know the N value. I've just calculated that, and I've been given the delta H. So all I need to figure out then is my Q. So that's how I know then I'm going to use this equation next. Be mindful, they like to ask this question in different ways. They might ask you to do things in different orders. So they might ask you, from the temperature change of the water, figure out the enthalpy. So they might have you going in this direction. All right? So be mindful you have to go forward and backwards with this math. So that's why I'm showing you guys how to conceptually think about my steps and which way I'm going to do it. So let's copy that equation down. We have the delta H is equal to the negative Q value divided by N. So several different choices on how I put this together. I can rearrange it first and set it to Q, or I can plug in the numbers and then move the numbers around to get Q. Do you guys have a preference? Don't really care? All right. Personally, I like to move my variables around while they are not numbers, because to me that's cleaner. All right? So if I multiply this by N, and I multiply this by N, the N's cancel out, and my equation then is negative Q equals N times delta H. So that's my own personal preference. All right, we know the N value. We know the delta H value. So now we can plug that in. So the N value that we got was for over here, and this H value is listed in my knowns. So again, that's why I like to list out my knowns and my unknowns. So my negative Q is equal to 0.07125 moles. Again, I like to keep my units there so I know what I'm doing. My delta H is negative 68.6 kilojoules per mole. So when I'm doing this math, the moles and the moles cancel out and I'm left with kilojoules, which is what my Q value is. It's talking about the heat released or absorbed in that chemical reaction. So I would have that number, see, times negative 62 or 68.6. That is negative 4.88775. But because the Q value is already negative, negative and negative, we can cancel those out. So I get my Q value is equal to 4.88775 kilojoules. Yes.
I have a question. Like, why is the Q from?
Why is
Q?
Q?
Yeah. Why is there?
So Q is just talking about the heat being released from that, or released or absorbed from that reaction.
Is that what it's Q?
Yeah. So remember that this value, the delta H, is talking about kilojoules per 1 mole. So if I had 1 mole of the reaction, that's how much energy would be released. But since I don't have a full mole, I have 0.07 of a mole, then I need to multiply these two numbers together so I figure out actually how much energy is getting released. We good? So that's my thought process. All right, keep going. All right, I'm going to start moving things this way because I'm running out of space. So now I can now do this Q equals M times C with the delta change of temperature. So let's do that one. Q equals MC delta T. So delta T just means change in temperature. So when I'm thinking about change in temperature, this actually means the initial temperature, the final temperature minus the initial temperature. We good? Okay. So again, let's plug in our numbers. We now know Q, and this is where the two reactions link together. Does that make sense? So this reaction here is linked to this reaction here because the heat from this reaction is using it to heat up the water. So now this is what I'm saying by 2 steps. So I know my Q value from previously. It was 4.88775 kilojoules. And then I set it equal to my mass. Now again, this is where people get tripped up. They grab the wrong mass number. In this case, when I'm talking about the temperature change, I'm not talking about the temperature change of the methanol. I'm talking about the temperature change of the water. So now I'm using the 100 grams. So that's what we have to be mindful of. There's 2 masses, and we got to be mindful when we use each one. In this case, we're using the 100 now. Are we okay with how I made that decision? All right. Then I'm multiplying it by the heat capacity of water. So the heat capacity of water is 4.18. And that's in joules per gram per degree Celsius. All right. And then I'm running out of space, so just be mindful we are still multiplying. In this case, we are multiplying by the change in temperature. The change in temperature, my final value is what's unknown, and I'm subtracting away my initial value. My initial value is 20.6. Are we okay? All right, let's start doing some math. So I have 100 times 4.18, and that's going to have my final T value is 148 final T minus, and then same thing, 100 times 4.18 times, in this case, 20.6 minus 861.8, like that. And then that's set equal to the 4.88775. Are you okay with that? How I did that math? Where? This one? So you see how this is times, and then there's the brackets? So I'm timesing 100, timesing by 4.18, and then I times it by that TF. So that's TF. I'm subtracting away the initial value. So that times that is that. Okay? Cool. All right, let's start putting some numbers together. So 4.88775. We are going to be adding that 8,000 to each side so that way it cancels out. Does that make sense? Sorry, I'm kind of squishing it onto the next question. They did not design this with enough space. So that cancels out. And then that is, see, did something wrong. It would be adding, not subtracting. All right, so I have now 8615.68775 equals to 418 TF. You okay with that? So all I did was, this is being subtracted, I've added it to both sides. So I've added these two numbers together. We good? All right, last step then is I need to get the TF by itself, so I divide it by 418. And I get my final temperature is going to be, that was barely any difference, 26.01169318 degrees Celsius. Let me check that answer for you guys, because I think they do want it rounded, but I'm not really sure how you're supposed to round it, because it's going to basically be the same answer. So let me make sure I did my math right. Level 3 chemistry things. You're going to make a mistake somewhere, because I did that yesterday, which is good. You guys can learn from the mistakes. So, let me see. What was this? Oh, it helps if you look at the right exam number. On. This looks like it's organic. What am I doing? Sorry, guys. Oh, I made a mistake. That's good. You guys can see it, and we can learn from it. All right, what did I do wrong? I see. Okay, let's backtrack. I know where my mistake is. Sorry, guys. Ignore that math that I was doing. Okay, we're going to start over. Not start over, just redo something. All right, let me get rid of this paper. I know what I did wrong. Sorry, guys. Cross out that last step. I'll show you. I see what I did wrong. I should not be plugging in numbers like that. Okay. Now I see what I did wrong. So let's fix that. So I am crossing out all of this here, my last step, because I know I made a mistake. So when we're looking at that final equation, we actually just want to use the delta T. Huh? Was it frozen? Oh, sorry. There. Okay. So my mistake was over here, trying to plug it in and do change of temperature. In fact, you just keep it as a delta T. So just ignore all this that I did here. Okay? Sorry. I should have double checked my work before I started. I should have checked it last night. All right, so we're still using Q equals MC change in T. We're just going to use change in T and leave it alone. We're not going to expand it out to, initial and final values. So once again, I want change in T by itself. So I'm going to divide by M and I'm going to divide by C. So those two cancel out. And so I have Q equals, change in T equals Q times M, divided by M divided by C. I overcomplicated things. So delta T is equal to the Q divided by M times C. And then we can plug in our numbers. So we know our Q value from before. Our Q value was that 4.88775 kilojoules. And then we are dividing it by our mass. Our mass was 100. I knew something looked funky with that. So that's a good lesson for you guys. When you're doing your math and the number doesn't look right, double check your work. And that's for all subjects. So that's in grams, and then we're multiplying it by the heat capacity of water, which is 4.18. Where's our units? Per gram. Sorry, joules per gram per degree Celsius. There we go. I knew something was looking funny. All right. That also checks out because my math, grams and grams cancel out, joules and joules cancel out. And so all I'm left with is per degree Celsius, which is what I want. And let me make sure that kilojoules, just checking my units. Double check my units. Oh my goodness, I made another stupid mistake. This is why we check things. All right. Another mistake that we're catching is I needed to, so again, you see why I'm saying units are important? I wrote that in kilojoules. This is in joules. And I was like, wait a minute, I can't cancel those two out. They're two different units. So we got to convert this into joules. So I times it by 1,000. So this should actually be 4,887.75 joules. I think that is the number I want. Oh, they've already rounded it. That's why. Okay. I'm not rounding it. Catching all of Mrs. Mistakes today. All right. So the joules now cancel out with the joules. The grams cancel out with the grams. I'm left with the degrees Celsius, and that's per degree Celsius. So now I have degrees Celsius again. All right. Now we're on the right track, team. So it'd be 4,887.75. I think my method probably would have worked if I had converted that actually too, because I forgot to convert in the other question. All right, divided by 100 times 4.18. There we go. That makes more sense. All right. So the change in temperature is going to be 11.69318. I'm not rounding my numbers because personally I round at the very end. Degrees Celsius. All right. We now know our initial value for our initial temperature. Initial temperature was 20.6. So if I add that 11.69, et cetera, together, I get my final answer. So we're going to add that to 20.6. And my final answer for my final temperature then is equal to 32.293188182. And then I'm just going to round it to 3 sig figs. That is 32.3 degrees Celsius is the final temperature. That makes more sense, guys. I think my method would have worked, but I forgot to multiply that by 1,000. But I don't know. Don't listen to me. Use this instead. This is better. I feel like there's probably another math error somewhere else because I said something was wrong with that. Cool. Are we okay with that? Did you get a different number? Okay. All right. Yeah, that's the number on there. Cool. Okay. So, some things to keep in mind with how the points broke down. The final answer, including the units and the significant figures, they are willing to accept anywhere from 2 to 4 significant figures in the final value. That got you your excellence point. So I eventually got to the excellence level there. Correct process with 1 error, that is what gets you to the merit level. And in fact, you guys could see that I did that too. So right here, because I forgot to convert this from kilojoules to joules, that error carried through would have resulted in me getting a merit. Does that make sense? All right, and then the last thing for the achieved is 1 step of the calculation correct process with 2 errors. So I have actually, the first time I did this is an example of an achieved because I made this mistake here. So I did at least 1 step correctly. So now you guys actually got to see an achieved, a merit, and an excellence level answer in my 1 lesson. So that's kind of good. Does that make sense? So just 1 step. So that's a step, This is all steps. That is an achieved. This here, if I forgot to convert it, that's an example of a merit. And then this is the excellence, is getting the right answer. So it should be an easy excellence point if you can do the math and you don't get confused. Unlike the one we did yesterday with the bond calculations, with Hess's law. Hess's law is really nice because you can idiot check yourself. There's lots of checkpoints there. In this case, there's not that many checkpoints, so you really need to understand your process. Are we okay with that so far? All right, just want to point out this second question here because, again, it is a common question. They say the standard enthalpy of combustion of methanol is slightly more exothermic than the experimental value provided in part 1. Explain 2 reasons for this difference. So that is a common theory question. The theory question is, we have 2 things. First thing we could say is that maybe we didn't insulate the beaker properly or insulate our reaction. And so instead of the heat being transferred to the water, it was transferred to the environment. So if it's transferred to the environment, it's not heating up the water, and thus we're not actually measuring that change there. So that's the first thing. Beaker's not insulated, there's no lid, the heat is escaping. So that way we're not actually transferring the heat to the water. Are we okay with that first point? The second point, why our numbers may not be what we'd expect, is because there's incomplete combustion. So combustion occurs because we have the fuel being burnt with oxygen. If you don't have enough oxygen, then you do an incomplete combustion, which is less energy efficient, and so you're not going to get as much heat. So that's 2 reasons why. The other reason is there's no standard conditions. So standard conditions is 25 degrees Celsius, 1 atmosphere of pressure. So if we're not at standard conditions, then you're obviously going to have slightly different numbers because everything that we have set mathematically is based on that number. So just something to keep in mind. And I'll link this onto Google Classroom and my site and stuff like that. Are there any questions? All right. So it is a little bit of a trickier version than Hess's law. Let me walk you through then what we should be working on. So just so you guys are aware of what I've set up. Mahi choice is up to you. There is some side pages you can do. Remember, I don't expect you to complete all of them. Just do what you need to until you understand. I am not 100% sure how good those side pad pages are when it comes to things like this, because it's just math. And I feel that with math, it's not like theory questions like the periodic table trends, but it does help to have that scaffolding and to understand how to write it. In this case, because it's math, you're better off just doing the math problem and then seeing where the mistake is and then keep working on it. So I'm not 100% sure how useful those are, but they do have some calculations on those pages. I think that actually goes to 88. There's a mistake there. Other option is to work on your no brain too small, which, like I said, it might be the better one. Just be mindful when you're looking at those no brain too small questions that you're flicking your way through it to find the ones that are the heating questions, because I haven't done the other versions. But you can, in theory, do the other versions. They're more or less kind of the same kind of concept. You have to divide it into 2 types of reactions. I've also put a CPR quiz, but only do that once you guys feel confident. Again, on Google Classroom, I haven't made a copy for everyone, so please make a copy when you do it and then hand it in so I know to check it, because I'm not going to check, all my lesson plans because they're a lot of work. All right, cool. That's us. You guys got the remaining 20 minutes to work.